Artificial intelligence doesn't progress on software alone. Every major leap in model capability is driven by advances in hardware built specifically for AI workloads. As models have grown larger and more complex, traditional CPUs and GPUs have struggled to keep up with the demands of memory bandwidth, parallelism, and energy efficiency. To meet this challenge, a new generation of AI chips is emerging. These processors aren't minor upgrades. They fundamentally rethink how computation, memory, and data movement work together. They are now shaping how future AI systems are trained, deployed, and scaled. Nvidia Rubin. Nvidia's upcoming Rubin architecture is one of the most anticipated hardware releases in the AI industry. Expected to arrive in 2026, Rubin follows the Blackwell generation and pushes Nvidia's long-term roadmap for large-scale AI training even further. Rubin is designed to support HBM4 memory and transition to more advanced semiconductor process nodes. Industry estimates suggest that Rubin could deliver performance approaching exascale levels for FP8 workloads, representing a substantial jump over previous architectures. This level of compute is critical for training the next wave of extremely large models that require massive parameter counts and long context windows. Whether or not artificial general intelligence becomes reality, Rubin provides the infrastructure required to experiment at unprecedented scale. It is less about a single product launch and more about extending the ceiling of what is computationally possible. Google TPU V6. Ironwood. Google continues to invest heavily in its in-house tensor processing units, and TPU V6 Ironwood reflects that strategy. Designed to train the latest Gemini models, Ironwood focuses on scaling efficiency across massive clusters rather than maximizing performance on individual chips. Google has previously stated that TPU V5 significantly improved training efficiency compared to earlier versions, and Ironwood builds on that momentum with higher throughput and improved energy efficiency. What sets Ironwood apart is its optimization for multimodal workloads, including video, audio, and long context reasoning. The real advantage emerges at pod scale, where thousands of TPUs operate together as a single system. This allows Google to train frontier models faster while consuming less energy per training step, reinforcing the idea that AI progress increasingly depends on system-level design rather than isolated hardware improvements. Nvidia Blackwell B200 Blackwell represents Nvidia's flagship architecture for the mid-2000s and introduces major improvements in memory capacity and low-precision compute. With support for hundreds of gigabytes of high-bandwidth memory and dramatic gains in FP4 and FP8 performance, Blackwell is built for modern AI workloads that prioritize efficiency. Blackwell's performance per watt improvements directly reduce the cost of training and deploying large models. Companies already use it for advanced language models, vision language systems, and autonomous agents that require real-time inference. In many ways, Blackwell marks a turning point where efficiency becomes just as important as raw performance. AMD MI400 series. AMD's MI400 accelerators represent the next evolution of its CDNA architecture. While full specifications have not yet been disclosed, AMD has confirmed that the MI400 series will use HBM4 memory and target extremely high bandwidth workloads. AMD has gained significant traction with its MI300 accelerators, which now power multiple large-scale AI deployments. MI400 builds on that success by improving interconnects, scaling efficiency, and overall performance per watt. For cloud providers, MI400 offers a credible alternative to Nvidia hardware, reducing reliance on a single supplier and encouraging faster innovation across the ecosystem. Tesla Dojo V2. Tesla's Dojo is a custom-built supercomputer designed specifically for training autonomous driving systems. Unlike general-purpose accelerators, Dojo uses Tesla's own D1 chips arranged into massive training tiles that scale across thousands of units. Dojo V2 improves thermal performance and compute density compared to the first generation, allowing Tesla to process enormous volumes of video data collected from its vehicle fleet. While Dojo is highly specialized, it highlights a growing trend. companies building dedicated hardware optimized for their unique AI workloads rather than relying entirely on off-the-shelf solutions. Intel Falcon Shores. Intel's Falcon Shores is positioned as a hybrid XPU that combines CPU and GPU-style computing into a single architecture. Built using a modular chiplet design, Falcon Shores emphasizes high memory capacity and bandwidth to support large-scale AI training. Intel has stated that Falcon Shores aims to close the gap in generative AI by focusing on efficiency and scalable system design. Several cloud providers are already evaluating it as part of future AI clusters, signaling growing interest in diversified compute supply as AI demand continues to surge. Amazon Web Services Trainium 2. Amazon Web Services unveiled Trainium 2 as a major upgrade to its first-generation training accelerator. Designed for massive distributed workloads, Trainium 2 delivers significantly higher training performance and improved energy efficiency. Amazon Web Services expects future models with hundreds of billions of parameters to be trained on clusters powered by Trainium 2. By developing its own hardware, Amazon Web Services reduces dependence on external suppliers while offering customers another path to large-scale AI training at competitive cost. Rethinking chip design. Cerebras takes a radically different approach by building entire silicon wafers into single chips. The WSE-3 contains trillions of transistors and hundreds of thousands of compute cores, eliminating many of the communication bottlenecks found in traditional GPU clusters. This design enables faster iteration and simpler scaling for certain workloads, particularly large language models and scientific simulations. National laboratories and research institutions already use Cerebras systems to explore models that benefit from reduced system complexity. Groq LPU. Groq focuses on inference rather than training, optimizing its language processing units for deterministic, ultra-low latency performance. Groq's architecture prioritizes predictable data flow, making it ideal for real-time applications such as robotics, conversational AI, and financial systems. As models grow more complex and context lengths increase, inference speed becomes just as critical as training throughput. Groq demonstrates that future AI systems will rely on diverse hardware optimized for specific tasks, rather than one-size-fits-all solutions. SambaNova SN40L. SambaNova designed the SN40L to serve enterprise AI workloads efficiently. Using a data flow execution model, the system optimizes how operations move through hardware, improving inference efficiency for large, full-parameter models. This approach is especially valuable in accuracy-sensitive fields, such as healthcare and finance, where quantized or reduced models may not be acceptable. Organizations report lower energy costs and improved deployment efficiency, highlighting the importance of inference-focused hardware. AMD MI350. The MI350 series serves as AMD's transition between current accelerators and the upcoming MI400 lineup. Built on the CDNA4 architecture, MI350 targets FP4 and FP8 workloads common in modern AI models. With improved energy efficiency and performance over MI300, MI350 is expected to appear in cloud environments that already support AMD hardware. It reinforces the idea that the AI hardware market is expanding beyond a single dominant player. AWS Inferentia 2. Inferentia 2 powers large-scale inference on AWS, offering higher throughput and better price performance than its predecessor. It supports advanced quantization techniques that reduce memory usage while maintaining accuracy, making it well-suited for production deployments of large language models. As inference workloads grow, dedicated serving hardware like Inferentia 2 becomes essential for controlling costs and maintaining responsiveness. Tenstorrent, Wormhole, and Blackhole. Tenstorrent develops RISC-V-based AI processors under the leadership of renowned chip architect Jim Keller. Its Wormhole and Blackhole products emphasize efficient data movement and scalable mesh networking. These designs support both training and inference, with particular interest from automotive and robotics companies that require predictable, real-time decision-making. Tenstorrent represents a broader push to diversify global AI compute infrastructure. Huawei Ascend 910B. Huawei's Ascend 910B is one of China's most advanced AI accelerators, designed for large data centers and national AI initiatives. While Huawei releases limited public performance data, independent reports indicate strong FP16 performance and high memory bandwidth. Ascend chips power language models, scientific research, and other large-scale AI projects, reflecting a global trend toward domestically developed hardware as demand for compute continues to rise. If you found this video useful, there's a lot more coming on the technology shaping the future behind the scenes. If you want to stay ahead of where tech is actually going, like and subscribe so you don't miss what's next.